Great. We can start lecture 24. That would be a lot of lectures. So this one is the one before the last lecture. The next lecture is the last official lecture. And these few lectures, we told you, you're not going to have homeworks. It's more for learning topics that will be useful for you. So we will have a closing session on Wednesday next week, but next lecture I'll talk about convolution, and that's the last one. Okay, I'm assuming you can hear me on Zoom. I shared my screen, and I'm going to start. So we're going to continue to talk about the classification problem, and we're going to extend it to soft margin and a nonlinear classifier. It's called support vector machine. And you see how it will be related to project 2 when you use radial basis functions, and we're going to see it again today. So we're going to cover 2 topics: the extension of the hard margin or max margin classifier to the soft margin. And then I'm going to show you an example that is not possible to solve. So I'm going to show you first an example that it's not possible to solve with the hard margin. Then we're going to extend it to the soft margin. Then I'm going to show you an example that you can't even solve it with soft margin. Then we do another trick to extend it to support vector machine, the Gaussian support vector machine. This particular soft margin, you can also call it linear support vector machine. A quick recap of distance. So everything started from hyperplanes, talking about dividing the space into 2 sides. We came up with a generalized formula for the distance to a hyperplane, given its basically normal vector, a vector that is orthogonal to the hyperplane, A, and an arbitrary point on the hyperplane. This y of x, for any point that even if it's not on the hyperplane, shows the amount of deviation, the shortest distance to the hyperplane. And then we normalized it by A because we talked about it. We don't want to scale the space. If your unit is 1, 2, 3, if the length, the norm of A is 2, it's going to make it 2, 6, 8, right? And that's not good. So this is the same problem, the same distance function. We are not changing the basic setup that we had. Then we posed a problem. I give you 2 categories. You know their inputs, their location in the plane, these circles and crosses that we have. One category is a red circle, the other one is the blue cross. Then we want to find a hyperplane. Here in the plane is a line that separates or classifies a new input to one of these 2 categories. That's the classification problem. So the model is a hyperplane, and again a line because it's 2D. We are given a data set. This type of problem usually starts from when you have the data. That's why having the data is so important. And there are lots of effort sometimes to just create the data set. And in some domains, you just don't have access to data. So then you just cannot simply solve interesting problems that you might want to because there's a lack of data. But assuming that we know a data set, n pairs of x and y, x values here are 2D locations in the plane, and the target values, the outputs, in the labeled data sets are +1, -1. So the distance function is continuous. It will give you a magnitude. It's a sine distance. It will tell you how far you are from the plane. But the way we can use that is to look at the sign of the distance. When you have the distance to the hyperplane, if the sign is positive, it's in one side. If the sign is negative, it's on the other side. Then it makes sense to talk about these labels that are not continuous in classification. They're discrete categories. And it means that it's related to that distance function through its sign. So we define the sign function to take the sign if you want to make prediction, and that was what we talked about last time. And for the hyperplane model, we had basically A transpose times X minus XC. Because A transpose times XC would give us a constant, we rename it to A naught, and this is the bias term. So the bias term, we talked about it, that is very important because if you set the bias to 0, we're only limited to models that go through the origin, and that's not covering all the possible solutions. In particular here, the line that generated the true data, when I simulated the data set, it does not go through the origin. So to get a good performance, we need to have a non-zero bias term here. Then we vectorized our parameters. So usually you're given a normal vector and a point, and then you form a hyperplane. In this case, we're given a bunch of points, x, and their signs to be what side of that hyperplane. We want to search for these parameters, a and a naught. When we stack them, we call them w. So the classification problem is about finding these parameters, given some examples in this data set. Assuming a particular structure for the model, which is the hyperplane here. You could say that I want to use a polynomial. That would change the problem. That's possible. Okay, and then we x bar, it means that we also append 1 to each x. So when we multiply w transpose by x bar, it gives us exactly what you see here. So this is just a matter of convenience. Then our maximum margin classifier was like this. We said that define the distance 1 to define one side. Anything on and above this value, we call it the category of +1. And anything on and below -1 was the other category. Now, it seems that the distance is fixed, but it is not. So there was a question that, how can you fix the margin? It is not, because we need to divide. If you look at the distance formula, we divide by the norm of this normal vector. Now, if you divide this by norm of the w, then that's the actual distance. So the way we change w, which is the value we search for it, it changes these margins. So they're not fixed. And then we convert this to what we said to mathematical constraints, inequalities. W transpose times x bar I greater than or equal to 1. That's for the category if y is equals 1. And the other constraint is less than or equal to -1 if y is -1. We could do something smarter. We can just multiply y by w transpose x bar I, and that would combine both constraints into 1. Because whenever y is negative, it will change the basically the direction of the inequality, and then we'll multiply the other side. Basically, if you multiply, what happened? I'm confused. Last time it made sense. So the first one is what we have, right? When y is positive 1, it doesn't change anything. When you multiply it, you still get w transpose times x bar I greater than or equal to 1. Now, for the other one, if you multiply it by y, because y is negative 1, you have to multiply both sides by a negative sign, right? We will make it like this. It will change this to greater than or equal to, and then we replace this by y my handwriting is really bad. I lost my pen today. It's really difficult to put a dot. Okay. It's a really big I, but you get the idea. So that will combine both of these constraints into one, which is because it's easier to program it like this. Now I'm using y in the book is L for label. You can change, some people use T for target. It doesn't matter, we can change the notation. Okay, so we got the constraints, then we formulated an optimization problem. Whenever you want to search for some parameters, you start thinking about an optimization problem. Really, the simplest problem that we can formulate is here is constraint because we have inequality. We can say that you can minimize 1/2 to keep it pretty, no other reason. You can minimize norm squared, just like when we were doing least squares or minimum norm problem. But norm squares is W transpose times W. So this is the simplest problem we can formulate. The cost function is norm squared. We want to find a W that is a small. Find a small W that also satisfies all the constraints. There's not just one constraint. We have n points in the data set. For every pair of the data that we have, input, output, we add one line of constraints. Namely, all of these points that you see here. All the red circles and blue crosses are, each of these points will add one line of constraint. So find a line, and by line we mean if you know W, you have the line, right? Find a line, find W that is a small, and respect the constraint of being on what side based on given labels in the data set. That's the idea. There are other ways to formulate this problem. There are other types of classifiers. You can formulate other programs. This is basically the classic way of solving this problem. Now, then once we formulated the problem, we talked about that this is actually a very standard type of problem in optimization. It's called quadratic programming. when you have a quadratic objective function, cost function, and constraints that are linear. Our variable here is w. There's no w squared. There's no square root of w, right? There's nothing nonlinear. This is a linear inequality. You can have equality too. That's not a problem. This type of problems are quadratic programs. And there are great solvers, and we can just define our problems and solve for w. No matter what level of researcher you are, freshman or professor, that's what you do. You do not try to implement a solver, right? Even in research lab, on the robots, whatever, whenever we have a quadratic program, we find a solver and solve our problem. Now, I'm not showing the result. That's for last time, which is basically what we had here. The pink line is the solution, which is not perfectly aligned with the ground truth, but it's very close. Now, we arrive at a very important question that came up last time as well. It sounds like that it's too good to be true, that in reality, these points are perfectly separated, and you're just going to find a line and classify it. That sounds like a very easy problem. And it is. It's a good problem to start from. And then let's see how we can fix it. Now, the truth is, in reality, you're going to have some overlaps. At the boundaries, these data points will be blended, right? There's no sharp, usually, boundary. Depending how noisy your points, your observations are, it can be very severe, right? You might have outliers if you are collecting data using a sensor or with some process that can introduce mistake. You might have outliers. Outliers are points that, for example, you get a point here, right? This can't be true, but in data it exists, right? And it's not easy to clean it up because you don't know if it's an outlier or not. Of course, if you knew it, you would remove it, but you don't know that. So now I leave it to you to try the hard margin classifier on this data. Should be easy for you. You just define the original problem in the first notebook, in the second notebook that I generate this type of data, and then see what happens. It doesn't work. Now, I don't remember if it doesn't give you a solution or give you a wrong solution, but it's not something that you can call it a solution. So it doesn't work. We need an idea to fix it. Which I've written here, but can you explain what do I mean by this proposed fix? Very intuitively, not mathematically. What do I mean by introducing soft margins, and we're going to call it the slack variables? Again, the problem is data points are blended at the margins. Looking for idea to fix it. Why they are blended? That's just how the reality is. Real world is messy. That's yeah, like what is the, where do you call an email spam? Now I personally started calling every email I get from the university spam. But that's my definition because it's just too many emails. I cannot separate the actual emails that I need to reply with the emails that is just for my information. But obviously, Gmail is not going to label them as a spam, right? It sounds like a very arbitrary boundary here. A lot of people, places contact us, right? Sometimes they are spam, sometimes they're not. So some of them are very obvious, like somebody emails me that there's $1 million I want to transfer to you. You're my only relative. I know I'm not that lucky, so I'm not going to accept this. So that's an obvious spam, right? So another one is a publisher is contacting me that there's a book. Are you interested to contribute a chapter? I mean, typically we consider it as a spam, but it's not actually spam. There's a publisher. It's just we're not interested, maybe. I'll be happy if my email label it as a spam, right? But Gmail is not going to do that. Because then every publisher that contacts me will be spam. So in reality, we can come up with other examples too, right? Sometimes you have clean data, that's fine, but those are usually maybe human labeled or something that is supervised in the sense that somebody carefully is labeling that for you, right? Which makes it very time-consuming to generate that type of data. So going back to the fix, so the hard margin was saying that find a line that perfectly separates them. Soft margin is saying that, well, how about we cut some slack for these boundary points and just let them be. Do not get so irritated trying to find a line that meet these constraints perfectly, right? Because then you change the line, and to satisfy one of the constraints, you lose so many others. So it's not possible. So the slack variables play this role that they give freedom to a little freedom to every constraint, so the optimizer, the solver doesn't get so irritated trying to satisfy perfectly all of them at the same time. That's what's happening here. So, and the slack variable is the standard term in optimization. So what we do, we say that find, again, this is the norm squared. Find for every constraint, every data point, consider a positive slack variable, right? It's non-negative. It can be 0. If the point is too far from that boundary, the slack variable is probably 0 because it doesn't matter, right? It's easy to satisfy that point. And it doesn't have any say basically in the solver at that point. So 1 minus this slack variable, and we have n of them. For every data point, every constraint, we have 1 slack variable. Then we stack all of them into a vector, call it, this is a scary Greek letter, it's called Xi. And it's our favorite. Makes our notes very professional and scary. So we call it Xi, and you can write it in LaTeX like this. X, I. And then take the minimum norm for that as well, because we need to make sure they're small. Find the smallest possible slack that you can cut for each constraint. Sounds like a great idea. And this lambda, because I have now multiple objective functions, right? This is an example of multi-objective optimization. W is one term, The slack variable now is a new variable that I need to search for. Each of them, they have an objective function. I need to optimize both of them at the same time. So it's going to be a trade-off, and the solver will figure it out. What's the downside? The upside is that now it will relax the hard margin. Can you see a downside here? So I was saying, by the way, lambda is constant. It's just the tunable weight you can set. So I draw a hint here. Instead of solving for 3 parameters, right, I need to solve for 3 plus n parameters. What if you have 1,000 data points? Now, instead of 3 parameters for the W, I need to solve for 1,003 parameters. That's a much bigger problem to solve, right? So it affects the scalability of the problem, but we have no other way. This is the fix. But it's fine, by the way, for maybe 1,000 data points, we can solve it. But if you have 1,000,000 data points, this is probably not going to work. Or maybe it does. You can try. I've never tested the limit of this solver. This solver is very modern, so maybe. But there will be a limit. At some point, you can't solve the problem if it's bigger than a certain limit. So we can do one more thing. Let's vectorize this and put it in a form that our solver expects to receive. You do not have to do that. Your solver might directly take this form. But this OSQP operator, splitting quadratic programming solver, expects a vectorized version. So the first thing we can do is convert all the n constraints to matrix vector constraint. Define a matrix phi to be n by 3, and each row is negative. I'm converting this greater than or equal to less than or equal to by multiplying a negative to the both sides. So define matrix phi. Each row is negative y times x bar transpose. You have 3 columns. W is 3 by 1. So phi times W as a vector, which will be n by 1, less than or equal to negative 1 plus c. This is equivalent of the constraint line. And for the other one, we are just saying that it should be greater than 0 as a vector, right? So what it means as a vector, I mean the same thing. I mean, each of them should be greater than 0 for c. It's just a change of notation, a style. Now we can do one more thing, because the solver actually wants it to have lower bound and upper bound. But when you have greater than 0, your upper bound is basically the infinity. You do not have an upper bound. So what you see here, I am stacking 2 objective terms into a quadratic form, right? Stack W and C into one vector. It's going to be n plus 3 by 1, right? So it's going to be this new vector transpose times this matrix W. Now, if you expand this, multiply them, you'll get exactly what you see here, right? If it makes you uncomfortable, I really recommend to just multiply them directly. At some point, your eyes will be able to catch why it's like that. Because, well, this is a diagonal, block diagonal matrix, right? Lambda I3 times W. And this is also a row vector, and you're going to get W transpose times lambda I times W. That's the first term. For the second one, you also get the second objective. I'm also combining the constraints into a matrix form, and we add any zero or identity as necessary to make it work. So QC is again greater than 0, less than infinity. The other constraint, because I multiplied -1, now it's less than or equal to -1 and greater than negative infinity. Another new notation is that 1 subscript n is just the n vector of all 1. Same true for 0. And this is a matrix of all zeros. Okay, so we need to do this, otherwise it's hard to, we need to define these matrices in the solver. We'll see in the notebook. So it is just algebraic manipulation at this point. We're not changing anything. Now later we will go over the notebook, but now when you solve the classification problem, although you have some outliers, or even on this side you have outliers, the soft margin will find the best trade-off, right? This is the best trade-off based on the quadratic program we formulated. Will it work? Most of the time it works, right? But if your point is on the boundary, there's a good chance we make a mistake classifying it. Which gives you some idea that maybe, depending on the distance of the point, I just label them unreliable, right? It's possible to classify them, but you're risking making a mistake. So the line is your decision boundary. Based on the new input, you make a decision to label it as blue, red, +1, -1. So that's the idea of soft margin classification. It's also called linear support vector machine, SVM. Is there any part of it that you'd like me to re-explain? Again, conceptually, this is more important than the algebraic manipulation. You need to take your time, go through it. We're training you to give your instructors in machine learning course a hard time. You will ask hard questions. You'll demand real answers at that point. Okay, so if you're good, we can move to next topic. I don't see any question in chat. Oh, yeah. Can you go over the OSQP solver one more time? Oh, I think I had the hyperlink somewhere. I'll do it. I'll go over it in a notebook, but also I have a hyperlink. Now I'll go over it very soon. It's good to give you an overview of the solver. We're gonna replicate these results in the notebook. I'm just showing you the final results now. Now, The soft margin was the first problem. We could come up with a fix. I'm going to give you another problem. What if data is not linearly separable, even if you use soft margin? For example, these blue dots are in this circular form inside the red dots. Good luck separating them with a line. Can you? You're having doubts. Maybe we can. Well, that's a good time to show you this. Are you ready for the truth? It can be unsettling. The obvious answer was no. You cannot find a line that's separated. It's a good time to go and watch Matrix movie again if you don't remember which pill was which. You might choose the wrong one. So, which pill you're going to take? That changes the lecture. It's interactive. We're going to decide what to do. Ben says, take the blue pill. Now, if you watch the movie, blue was remaining in the contented ignorance. I think that was blue. Oh, you know. So you're happy. Okay, you want to be happy, and that's fine. So my answer to you is that you can't do that. So feel free to ignore the rest of the lecture. There will be no exam on these topics. Anybody wants to take the red pill? Oh, you want red? Okay. So we're going to tell you the unsettling truth. You're ready for it. These are the final lectures. Now, what if, this is the idea, it's a crazy idea. What if you lift your data into a higher dimensional space, vector space, like here from R2 to R3, and now it's linear. Instead of a line, a plane, what if it's like this, right? This is a conceptual, a canonical example that shows that you can. What if you have a feature map like phi that lift your data into 3D, and then you only need a plane, and then it is solvable. And our formulation was general. The inputs were 2D, it was a line. If you can do it for 3D, 4D, any dimension. So if you can separate it in the lifted problem, then you can also convert it back, and then maybe that gives you something like this, a circle that separates data. So if you go to a dimension that is high enough, it is linear. How high? Infinite. What's the feature map? We don't know. Do we need to calculate it? Leads to two ideas. Yes, neural networks. Neural networks explicitly, I'll have a remark, calculate this. No, kernel methods. It's implicit. You don't see it. It's done implicitly. Now, the math behind it is quite involved. And again, this is something that you can demand from your machine learning instructors at the time to explain it to you. But the math behind it is something that makes graduate students usually uncomfortable too. But the trick is something you can learn and use. You do not need to dig too deep into the problem at this point. So here's the trick. Our function, the outputs had this form, right? The hyperplane that we were fitting was W transpose times X bar. And then we wanted to look at the sign of it and see which side it falls. define a feature map that takes your x bar, oh, that 1 is not important, right? Because we appended 1 to every vector for the bias. Take the input and maps it to a feature space, this phi. We don't know what it is. Then use those features. For example, it can be polynomials. At this point, you know something about it. In your project 2, you were doing this. You use polynomials, then you use RBF for fitting a surface, right? This is the same thing. So phi can be a polynomial. But we're going to use RBF here. Then you define a new function, instead of W transpose X, something that is weighted sum of every feature vector. And you have, if you have n inputs, you're going to have n plus 1. Why? You pick one of them to be the bias. You can set the feature map to 1 to act, and that will act as bias then. Usually it's helpful. It's given the same intuition that we need bias to cover all possible models. Then you will have alpha transpose times phi instead of W transpose times x bar. Now notice that previously W was, in our example, 3-dimensional vector, only 3 parameters. This alpha is n plus 1. Again, if you have 1,000 points, you need to estimate 1,000 plus 1 parameters for this new model. And then we added another 1,000 slack variables, right? So we're at 2,001 variables now. So the intuition is that you can do that for any problem, given enough sufficiently high dimension. And the way it works that for every data point you have, you add a dimension in this formula here, okay? So what is phi? You don't need to design a particular feature, although you can. The most common one and one of the most successful feature map is this RBF function. It's also called Gaussian kernel. This function is also called kernel. You can call it Gaussian, RBF, sometimes also a squared exponential, doesn't matter. It's an exponential function. You need a center, right? Xj. You have a bandwidth S, the scale, and the input is X. This is exactly what you did in project 2, right? So we do this, and we have a new problem. Instead of W, now we are going to solve for alpha. We have m alpha. Here is n plus 1. So replace W with alpha. And phi is, instead of negative y times x transpose, is y times phi transpose. Now you know that from your project that this is not, phi is not a single value, because for every input, right, you're going to evaluate it with all other inputs. And that will give you a very long vector. So this phi is going to be n by m. You have n inputs, right? And for every input, you evaluate it with all other inputs. That will make it n by n. But also you pick a constant 1 basis as bias. That will make it n plus 1, right? So then phi is n times n plus 1. I'm very proud of this. I wrote it with mouse instead of pen. So that extra 1 is for the bias. That phi term is just constant. So what do we get? This is called Gaussian SVM. It's nonlinear. Because of that exponential basis, it's not a line anymore. If you implement, now by the way, this is, although it's nonlinear, again, just like the least square regression we did, is nonlinear in these basis values. It is still linear in the parameters that we want to solve. It's still quadratic program. We didn't change anything about that part. So we only changed the feature map, right? Only mapped each x to a feature map. And then change the style of your function to be this new y. So this is still although it's different size, go and compare it to see the difference. It's still a quadratic program, so we can solve it. We'll see soon in the notebook. When you solve this problem, you have, here inputs are 2D. When you solve this, this will give you a function that for every point in this plane, it will give you a value, this surface. You plot the contour of that function. These are, you have a surface, right? And then get planes at constant heights to cut through your surface and overlay all these curves, intersections on one plane, zero crossing. When z is 0, it will give you the contour plot. These boundaries, these curves, are called decision boundaries. Why? Because if you take any of these curves, you can say here, for example, inside is blue, outside is red, right? But you need to make a decision which one is your decision boundary. Now, in this particular example, we are going to use the sine function again, right? Map that surface that we have using the sine function. You will get these boundaries. So anything beyond the dark line, which is the outline, you get -1, right? Now the boundary is very colorful because that's where the sign is changing, right? And the white area is just the poor choice of color map and background. This actually, there's a boundary here too, right? It's just when the sign is 1, the color is white. So the inside is +1. Now this is very unusual because this is a nonlinear classifier. It wasn't linear, and it will find any shape, right? You can make it twisted, you can make a butterfly, whatever you want. Any shape, it'll find it for you. We should have put a Michigan M here probably. Maybe Trippy can make it for fun. I thought you'd be more excited. Nonlinear classifier, this is so cool. I was very happy when I implemented this. It's always satisfying. Now before, neural networks are old. They're from 50s and 60s, but I mean, these methods always, for one or other reason, they surface again, right? Before, in 90s and early 2000, this method was your default classifier, right? Now it's been about 20 years, maybe, but these methods were really huge at the time, just like deep learning is hyped now. Now, what's the difference? These SVM types are called kernel machines. Kernel is that feature map, the RBF. SVM is one of them. There are many other ones that you can learn in a machine learning course. The feature map here is implicit. You do not need to define a particular type of features, which makes it nice. You just evaluate every input with every other input to build that data matrix. That's what you did in project 2. In neural networks, it is explicit for every layer of that network. You probably learn later. If you know it already, you might follow what I'm saying. You have a bunch of layers. Each layer is a finite dimensional vector. Ultimately, it's a vector of numbers. You're after explicitly learning a feature vectors with a predefined dimension, maybe 500, 1,000. So the act of training the network is automatically from data finding that, because hand design will go nowhere for any meaningfully large problem, right? So we learn these features from data automatically. That's why they're powerful. But it is explicit. And once you have that feature, learned it, then you build a classifier or regressor on top of that to fit a function to anything you want. So they are different in that sense. And the reason this is now the mainstream is because it has better scalability. The way it works, it's scalable to a very large number of data points, millions, billions, because you can use mini batches to train the network. And that's actually enabled by parallel computing, because 30 years ago, we didn't have GPUs like this. Who knows? Maybe quantum computers will bring back the kernel methods. So the math behind it is closely related to quantum mechanics. Now, another insight is that on the surface, these are competing methods. People are, fighting, and which one is not much fight anymore, but which one is better. But they're actually complementary. A lot of methods that people think they're competing, they're complementary. It is usually the case that you can combine a kernel machine with a neural network. So they have complementary roles. All right, so so in project 2, another remark, we downsample data, right? If you go back and look at it now, we maybe use 1% of data to do the regression. It was good, it was working. But so the reason we did that is the scalability problem. Okay, so before we switch to the notebook, do you have any questions for this part? Now you're all expert in kernel methods. But once you are comfortable with the general idea, there are very good libraries, right? You don't need to implement SVM. You actually pass your data to the library, and that will do it for you. Okay. So let's go to the notebook. Next lecture, next Monday, I'll talk about convolution. How we can remove noise from a 1D signal and do edge detection in the image using convolution, and that will be just multiplying a matrix by another matrix, basically. Let's go to the soft margin. Oh, we wanted to talk about, Luke asked about So OSQP solver, you can go to the website. It has documentation, people who are developing this. That's their job. They're expert in this field. That's what they do. Not every engineer and mathematician develops solvers, right? Some of them, that's their job. They go to work, they think about how to make a better solver. Like I don't do that, for example. So a lot of people behind this, and a lot of places use the solver. The nice thing about it is that it has documentation. So you have a quadratic program, you have some constraints. So it wants you to define your problem like this, right? That's why we had so many small constraints. I had to construct one big giant constraint using matrices to define lower bound and upper bound. So you know you need to define P, Q, L, A, and U. Once you know that, your program is set and you can solve it. It supports several programming languages. Let me find. Now, these are nonsense to you at this point. Unless you take an optimization course, talk about duality. So the SVM I taught you actually, in practice, is solved using its dual problem, but that's way outside of the scope of Rob 101. That's usually taught in graduate courses. Interface. Okay, so now the nice thing about this solver is that, now we use Julia, and Julia is catching on. It's a good language for scientific computing, but the dominant language for machine learning, for example, is Python still. Or some people use MATLAB when you use control. The statisticians use R, for example, usually. If you're a serious programmer, use C, C++. That's the hardcore language. For real-time robotics, we usually need C++. But it's very, of course, it's harder to use it for prototyping. If you want to test an idea, Julia is really great, right? So in any case, if you work on any of these languages in your project, you can still use this solver, which makes it very convenient. You just need to go to the documentation and see how the API, application programming interface, is defined, and then use it. In Julia, it's very easy, the way we have it in the notebook. So if you have more questions about the solver, I should tell you, ask the developers, but you can post it on Piazza too. We will try to answer it. Okay, so I add the packages again. If you don't have them, you need to install OSQP and Compat, which will add sparse matrices for you. I define my problem, and here I'm generating data. Now this part is just a random idea to generate data. The way I do it is not important. You can change it. Then I visualize it to make sure it's reasonable for the test problem that I'm trying to solve. Here I'm defining my, oops. So in the solver, I'm defining P, Q, A, L, U, right? Now, the way I'm defining this, I write it down on the paper or here in LaTeX Markdown. I write this program, then I know my P matrix, Q, for example, here is 0, right? This is A, L, and U. That's why it's important to write it, because then I can code it easily based on what I have. Looks like I have some problem loading plot package. We should be able to solve it. We don't need to visualize it to solve the problem. Let's hope this works. Okay, so when I solve the soft margin, you see the output is it's almost hard to look at it. You don't want to look at it. Now, the way I know which part is the one I want, what is the part I want is your vector, right? The first 3 parameters is W. All the other one are the slack variables. We don't particularly care about the slack variables. We only care about the first 3, right? So you can throw away the rest. But it's interesting that you can see for most of the points, the slack variable is almost 0. These are points that are far from the line, the boundary. Occasionally, maybe you have some large value, right? These are points that, for example, here with 0.65, right, subtracted from that one that we had, it's making room for that point that is possibly is misclassified to be there, and the solver is not changing the solution because of that, because now it's accommodated using this slack variable. So again, the first 3 is our solution. So it's still fast. This is a still small problem. I probably won't be able to visualize it because I don't have the plot package. But we had the plots in the PDF, so it's the same thing. So this one is the SVM version, the Gaussian SVM. The difference is that now, instead of X, I have this feature vector, phi. I have phi matrix. I'm still calling it W, but this is actually alpha. It's not 3 vector, it's an n+1 vector. Let's generate data. See if we can plot it. Now, this part is exactly like your homework. Now, this probably will work for you. I was running it at home. I don't know why now. Another laptop, not this one. I would never give you a code that is not tested. You know me by now. So this part is exactly similar to, I might have actually copied from your project notebook. It's very similar to that project that you define an RBF function, right? And then you define a row for that. And then you build your regressor matrix phi by filling in each row. So that's exactly what we're doing here. But the first element of each row, the entire first column of this phi matrix is 1. That's the bias basis, basically. So it's n plus 1. 1 is this one bias term. So the phi is 1, but alpha is not. So that will be the bias. So we fill in, and I chose S to be 1. So that's how I built the phi matrix here. This matrix here. And if you know that, then 0 and identity is just something you can fill in. For lambda, I choose 1. You can change it and see how it changes. This is tunable. And we call it hyperparameters because it's not like alpha or Kc that is parameter of the model. It's a parameter that we tune just for the optimization. S is similarly called hyperparameter for the same reason. I don't think I defined this yet. So I define my problem here, and once you have your P, Q, in this case phi, A, L, U, you create a model from OSQP. This is my problem. Then you set up your problem with this syntax, problem, semicolon, then define P, Q, A, L, and U. Then you can call solve by passing your problem to the solver. You need to use this exclamation mark. And that's it. You have the results. Results.x is your solution. So the way it works, the solver, basically this whole vector that is a stacked version of W and C, that's called x. That's your variable. The solver does not separate W or C. That's just how we know it is. Now, in this case, which one is the solution? I won't be able to visualize it because of that error, but alpha itself is a very long vector here, right? So the first, we know the dimension of alpha. The first part with the specific dimension you know is your alpha. The second part is the slack variable that you don't need. Now, for this version, we need to create test data, because the way this basis model works, we need to, once we know alpha values, we need to query. Where do we want to know the output? That's exactly what we did in project 2. So I create the test set as just a grid that covers all my data points. This is just, these are equidistance points that I placed on the grid. Once I have my test points, many points on the plane, I take alpha here, you see here, the first, now I know my data, I had 200 data points, so from 1 to 201 will be my alpha. I get the regressor matrix using the test points, and I use my data as centers of RBF functions. So the output will be this phi matrix times alpha. That's how I can query using the learned alpha values. Then we can plot the contour, and here I get the sine of it to create that. Let me try again to see if I can fix the package. We've seen the figures in the PDF. It's nice if you can run it here. Maybe I don't have the, but this is strange because I used plots before in previous lectures. Oh, I need to. Maybe I restart the kernel. That should be your first solution in any software problem. Have you seen IT Crowd, the TV show? It's an old British comedy, it's funny. They're IT people, whoever calls, they say, have you tried turning it off and on again? IT Crowd, right? Okay, let's try again. Can you run it? I think you guys doing other work. It's a sad moment. And I realized you're working on other projects. Maybe somebody else can run it. Because I could run it on my other laptop at home. Same Julia version. Okay, this is fine. No luck. I give up. It's definitely something wrong with my laptop. You should be able to run it. Now, we could try it on Illumidesk too, but that's something you can try. Okay. I could run this last time. So strange. Last try. But the lecture is finished. I'm just too persistent. Do you have any questions? We have time, plenty of time for questions. So this wraps up the classification.